So good morning, everyone. Welcome back. I hope none of you got scared off by the meeting not existing until 2 minutes into class. So when we were last together, we introduced Stokes Theorem, and Stokes Theorem is sort of a 3D version of which other theorem?
Green's theorem?
Exactly. Stokes Theorem is a 3D version of Green's theorem, and like it even almost looks the same. If it's described the same, it's just on a higher dimension. And so we're going to continue today working through a couple more examples with Stokes Theorem, making sure we're repeating the kind of the interpretation and how to understand it. But before we go into a new example, I wanted to go back to the example we ended with in class yesterday and point to one nuance that I had glossed over. So here's the first example that we did yesterday, or the one example we did yesterday. And I realized this morning that we forgot to do this step where we verify the orientation. And in this case, it won't make a difference in the result, but I believe in the next example it will. And so I want to make sure that we address it on each example. So let me see if I can be clear on what I mean by verifying the orientation. So if you go back to the picture, notice that in the picture, all of the vectors, the normal vectors, are pointing out. So these would be all of your n vectors, or we find those n vectors by looking at RU cross RV vectors. And so in order to verify the orientation, and when I say verify, what I want to do is I want to make sure whether my math matches the drawing. And specifically, when I check the math, will it correspond to these outward aimed arrows, or will it be the other normal vector, which would be pointing in? So I want to make sure that I have the dark, maroon vectors versus the red ones that would be pointing in. Does that make sense?
Is this what we mentioned it yesterday? If it was negative, then it was just
exactly.
It was
exactly. So we're just going to negify our result if we happen to have the wrong orientation, but we need to check to figure out whether we need that negation. So here's how we do it. So notice that all the vectors that we want are pointed up or out, so to speak. So to check, what I'm going to do is I'm going to come to this place right here. Right here. So where you have the RU cross RV, and what we want to do is we want to determine whether or not this is pointing basically up or down. And so I'm going to pick some nice UV values. What would be some nice UV values?
3 and 3.
Maybe even nicer than that.
0 and 0.
0, 0.
0, 0, really nice, right? Say 0, 0. And so what that's going to tell us is that our n vector, which is equal to our RU cross RV vector, it's not exactly the same, but I think it's close enough that I think that'll work. Because the n vector is a unit normal vector and RU cross RV isn't necessarily a normal vector, but so it's actually just proportional. I gotta be a little careful. What would our n or our RU cross RV vector be in this case?
0, 0, 1.
0, 0, 1, good. And is 0, 0, 1 point up or down?
Up.
It points up. So is the orientation correct?
Yes.
Yes, so yes. So we verified that the orientation is correct, and so the sign of our result is going to be correct.
Do we need to check only one point?
Yeah.
Okay.
Because it's the oriented surface, you're going to get the continuity. So as long as we checked a point that corresponded to a point within our region, then just checking one point will be sufficient.
Awesome. Thank you.
Yeah. Any other questions about this? And I just want to make sure that I'm being mathematically correct. Remember that our n vector is defined to be RU cross RV divided by the magnitude of RU cross RV.
Quick question.
Mm-hmm.
So since the orientation points up, does that mean it's positive?
It means, let me just finish this one thought and then I'll get to that, Titus. So the key part, the denominator is always going to be positive because there's a magnitude there. So here you can see why I'm focused in on that numerator RU cross RV, even though n is just proportional to that vector. So I hope that clarifies it. Titus's question is, if the orientation is pointing up, will it always be positive? Often, but not always. There's a key phrase, which I'm hoping is clear.
Is it like
question
out of that? Sorry, go on.
So notice right here that we say that the paraboloid is oriented upward. So this tells you that up equals positive. That's kind of a weird way to say it. If we go to the next question where we're going right here. In this particular case, notice it says with given orientation, and the orientation, notice in this case, is around a line integral, and the flow is this direction. So using your right hand rule, which way would be positive? We'll give you the positive circulation. So it's kind of around, but using your right hand rule would point which way?
Other way?
Yeah, it would point down somehow, right? So in this case, it would be positive by the right hand rule. Did that make sense?
Yep.
Okay. And then in the last question, we have oriented in the direction of the positive x-axis. Oops. Gotta be a little clear on my drawings. Boom, boom. Direction of the positive x-axis. So that would be telling us that this direction would be positive. So there's going to have to be something in the question that's going to tell you about the orientation. Did that answer your question, Titus?
Sure did. Thanks.
Very good. Good question. Any other questions before we proceed? Very cool. All right. So speaking of cool, let's look at this cool note. So cool note. So if S1 and S2 are surfaces with the same positively oriented boundary C, then for any vector field F that satisfies the hypotheses of Stokes Theorem, we have that the circulation around, notice here it's S1, of the curl of F dotted with NDS, which would be the circulation, would be equal to the circulation across the surface 2. So you're going to get the same result. And this might seem a little bit strange to see in theory, but it's actually pretty easy. So imagine that you have some space curve C, and you're trying to figure out what's going on around C. So maybe your S1 is the surface that's going something like that. Is that do you guys, is that clearly 3D for you?
Yeah.
Okay, so this would be our S1. So we're saying that the circulation around C would be equal to the whatever you get from this double integral across S1, but would also be equal to what you'd get if you went across S2. So basically, as long as the boundary stays the same, you're going to get the same result. Okay. Questions about that picture? So super practically speaking, what this means is that if we went to the previous question, the long example we did first, notice we were comparing the line integral that was around C. We found that was 12 pi, and we compared that with the surface integral across the paraboloid, something like this. But what this theorem says is there's another option. We could have actually just calculated the surface integral across the disk and just use that disk at the base, the green disk at the base, and we would have gotten the same result, which would have probably been even easier than either of the other two options. Questions? Very good. All right, so let's look at another example. And before we start, let me just show you where we're going. So notice that in example 2, we're starting with a line integral. This is in the Stokes Theorem section. So what are we going to turn this line integral into? What are we going to turn it into?
Double integral?
Not a triple, but a
surface integral.
A surface integral. So we're going to turn this thing into a surface integral. Okay. And then in example 3, we're going to start with a surface integral, and we're in the section on Stokes theorem. So what are we going to turn this one into? Not everybody at once. So here we've got a surface integral. We're in the section on Stokes theorem. And so Stokes theorem is going to allow us to write the surface integral as a
Line integral?
Line integral?
As a line integral, exactly. So we can go either direction. So that's kind of where we're going. That's the big picture. Now we just get to work through all the weeds. All right, so example 2 says we want to find the circulation around C of f dot dr if C is the rectangle in the plane z equals y with given orientation, and f is this thing there. And let me switch over to the doc cam to actually work through it. So our our curve C that's given is this one here, and notice the orientation like that. And so if we want to calculate this line integral, what I notice right away is I go, if I want to calculate this as a line integral, what am I going to have to do first? What's the very first step for every line integral?
Parameterize.
Parameterize. And how many different parameterizations am I going to have to use?
4.
4 parameterizations. And I don't know about you, but I'm not a huge fan of parameterizing 4 times if it can be helped. So I look at this and I go, I don't want to do 4 parameterizations, but I'm stoked to be able to have some options. And so what I'm going to do is I'm going to at least try. It might not make things better. I might be stuck with the parameterization, but I'm going to at least ask myself, am I any better off by going over the pink plane there and using Stokes theorem? So this would be equal to the surface integral across pink S of the curl of F dot N ds. This is big S. And again, my reason for doing this is because parameterizing 4 times, while not difficult, is at the very least tedious. And so I'd like to avoid that tedium if at all possible. So we don't know if it's going to work yet, except for the fact that it's example 2, so it probably will. So let's try. So here we want to evaluate a surface integral. To evaluate a surface integral, what's the first step?
Parameterize.
Parameterize, exactly. I open up the chat, so if you want to respond to those questions by chat, you can do it that way. All right, so we're going to parameterize. What are we parameterizing? Which thing, yellow or pink?
Pink.
Pink.
Yeah, so we're parameterizing pink here, right? So we need 2 parameters because it's a surface. So we're going to have r of u v equals, and this is the plane z equals y. So what's our parameterization?
Is it gonna be 0t?
There's going to be 2 parameters, u and v. So you're definitely going to say again, Vu?
UVV.
U, V, V. So we're saying x equals u, v equals, or y equals v, and z is equal to y. So z is also equal to v.
Mm-hmm.
That makes sense?
Yep.
So we parameterized, and this would be on, it's a little tough to see in the pictures, but this would be the u values. Remember, this is our x, and our x's are living between 0 and 1. So 0 less than or equal to u less than or equal to 1. And our v's are living between 0 and 3. Again, a little tough to read on the picture here, but that's where our parameters are living. What's the next step?
Find the curl of F.
Before we do that, we're trying to stick to a very consistent process.
Okay. RU cross RV.
Find our RU cross RV, exactly. So step 2 is going to be find n dot ds, which basically amounts to finding RU cross RV. This is not a... Okay, so we need to find RU, not our U, but RU. So RU will be 1 0, 0, RV, 0,
0, 1, 1.
Yep, we like this. This is looking good. And so we used our shortcut of just going straight to the cross product below. So we're going to have 0, and then looks like we're going to have a, hard to see here, a -1 I'm seeing. That was 0, that was 1. This one's going to be a +1. Questions about this so far? Okay. And at this step, we need to pause. And what do we need to do?
Verify our orientation.
Exactly. So here, we're going to check our orientation.
Wait, how do we get -1 again?
Because it's the middle term in a cross product. So you have the +1, but you have the negative bit from that determinant.
Okay, yeah.
Okay, so to check my orientation, I'm going to quickly sketch my picture again because I think that'll help you see what's going on. So my picture looks like this. And we want to orient that thing. The C is oriented as this direction. And I can pick any U and V, and I'm going to get the same RU cross RV. So that's not very exciting at this stage. Which direction is this vector pointing? It's like it's pointing
out of the plane, like up left.
Yeah, like up left, exactly. So it seems like it's pointing something like this way. Okay. But if you think about your right-hand rule would say we want that vector to be pointing which direction?
Down.
Down.
So we want it to be pointing down. So we checked our orientation, and we have our orientation is backward, right? So since the orientation's backward, what are we going to do when we actually set up this this integral? We're going to then
scale RU cross RV by -1.
Exactly. We're just going to change all that signs to account for the orientation. All right, so step 3 is we're going to substitute and integrate. And as part of substituting and integrating, what's the first thing that we need to find here? Like we have to substitute, it's a little hard to see way up here. We have to substitute in for curl F and for N and for DS. We already know what our NDS is. Okay. That's the RU cross RV du dv. But we want to substitute in for curl F, which means we need to do what? We need to find curl F. So we need to find the curl of F. So remember, this is the del operator cross F. Or in other words, it's the partial with respect to X. Oh, I didn't follow my own advice. partial with respect to y, partial with respect to z. Something like that. We're just taking a determinant now. So it looks like we got 2yx minus 0. And then y squared
minus 0.
minus 0. Thank you. And 4y cubed
Minus 0.
minus 0 again. So we have 2yx negative y squared 4y cubed. So this is our curl. So we should now be able to put all of this stuff together and let's see. So this tells us that our line integral which is equal to the surface integral is equal to the double integral across, now it's the region R, of, we've got to substitute in for this quantity. So remember, x is equal to u, y is equal to v, z is equal to v as well. So this will be 2uv minus v squared 4v cubed dotted with, what do we come up with, 0, minus 1, 1.
You've got to flip the orientation.
Yeah,
And then we've got a negative out front, exactly, for the orientation. So, good catch. And then this is all going to be dA. Questions about where this came from before we actually go through and crunch it? Very good. So we have negative double integral of, I think I've got a v squared plus 4v cubed. Yeah. du dv. The u's are going from 0 to 1. The v's are going from 0 to 3. There's no u's anywhere in sight, so that's kind of convenient. So that'd be the integral of 1 from 0 to 1, which is just 1.
Stays as it is.
Yeah. And then we have negative v cubed over 3 plus v to the 4th from 0 to 3. (27 over 3, which is 9, plus 3 to the 4th, 81, or negative 90, all told. Whew. Questions about that? So I think what you can probably see is that there's a fair amount of steps here, but it's not actually that difficult. It's more just about going through the process and kind of following along and seeing where it takes you. Going back to the original question, why was it that Stokes' theorem was advantageous to us on this particular question? Like, what is it that it helped us do?
Cut down on parameterization and the number of steps and stuff.
Yeah, exactly. Thanks, Damon. So we could have done 4 different parameterizations and evaluated 4 different line integrals. Or in this case, we just evaluated one surface integral. So it's sort of a trade, like whichever one makes you feel good. Very good. Question?
So will we have been able to use Stokes' theorem on, say, the previous assessments?
You could have used, I'm trying to think of where it would have applied. So I think the place where it would have applied would have been if you'd had a space curve in 3D, something like that, then you could have used Stokes' theorem. There were cases where we had, I think we had things like rectangles, but they were just in 2D. And we already were able to simplify these ones by using Green's theorem. So it might have helped you on a previous assessment, but it probably wouldn't have helped a lot, simply because we didn't have that many 3D closed curves where we were trying to find the circulation. Good question. Cool. All right. One last question. So we want to use Stokes' theorem to evaluate the surface integral of the curl of f dot ds for the given field. So a couple notes about this question before we switch over to the dot cam. So note 1 is that if you see curl of f showing up inside a surface integral, this right here is a hint. And specifically, it's a hint to try Stokes' theorem. So for those of you that have looked at the final exam assessment, one thing you'll probably note on the final exam is that I tend to try to get rid of those hints. And so on the final exam, if the same question had shown up on the final exam, I would have just said, evaluate this thing right here. And I wouldn't have told you how to do it. But the reason why I might be comfortable doing so is because the simple fact that that curl is within that integrand is already a hint that you should consider using Stokes' theorem. Does that make sense? Very good. The second note before we work on this is about the differential element here. And I simply want to remind you that d big S with the vector quantity over the top is the same thing as n d s without the s over the top. So you might say, well, Dust, that's great. I don't remember what the s is for. So I don't blame you if that's your situation. So this s here, that thing is telling us that we're talking about a differential, like a small patch. It's the differential surface element. And so maybe you guys remember how those things worked. We had some sort of a surface, and we chopped it up into little pieces. And we said each of those DS's represented one of these little patches here. At least when the patch size went to 0. And the N is giving you, this N part here is telling you the orientation. It's saying we have an oriented surface, AKA not a what?
Mobius strip.
Not a Mobius strip, exactly. So DS with the arrow over the top is saying we want to have oriented patches. Good on the notation and the hint? Very good. All right, so let's work through this question on our work along. So we want to evaluate the surface integral of the curl of f dot ds for this horrible looking field. And we're at the moment, we're already feeling pretty terrible about the whole situation. And so if we want to, and notice, if we want to follow the surface integral, what do we need to do? What are we going to have to do to this f? We're going to have to find the curl of this horrible thing. And so for me, when I take a first glance at a question like this, I get like this bad feeling in my stomach that goes like, this is terrible. Like there must be a better way. So good news, there is a better way. Let's try Stokes theorem. So we're going to take that original surface integral and we're going to rewrite it as which kind of integral?
Line.
Line.
Line integral, exactly. And so this will just now be f dot dr. And before, some of you are probably looking at the notes, we had this this picture. It was something like this. And so our surface that we were interested in was this one, kind of the outside of the cone. But the actual, when we switch over to a line integral, we're just going to be looking at the boundary of the cone. Does the yellow show up? Can you see that?
Sure can.
Okay. And so since this is our yellow curve is here, we need to make sure we have the right orientation on like which direction are we going to go around that yellow circle. And so do you want to travel around that circle, I don't know, counterclockwise or clockwise? How do we know? One answer could be look at my notes. What did you say, Vu?
The question gave us.
So yeah, so the question said in the direction of the positive x-axis. And so what is it that will tell us if it's in the positive x-axis? We need to use the
Right hand rule?
Exactly. So we need to use the right hand rule. I'm always afraid that I'll accidentally use my left hand when I'm using the right hand rule. But anyway, so we're going to curve around this way. That will point towards in the direction of positive x-axis. And so our curve right there will make sure we get the correct orientation. Okay, so we have our picture. What do we need to do next?
Parameterize.
Parameterize, exactly. So parameterize. And so how many parameters are we going to need? 1 or 2?
1.
1, because we're parameterizing a curve and not a surface. So we'll have r of t equals, this is going to be a circle, and it's a circle with radius 2. So we're going to have 2 and then 2 cosine t, 2 sine t on 0 less than or equal to t less than or equal to 2 pi. Okay. We need to double check our orientation of our r of t. And so I want to make sure that I'm traveling the correct direction. So if I put in, and think about it, if I put in t equals 0, if I put in t equals 0, I'm going to be at 0 or 2, 2, 0, which would be like right here. And then I could put in t equals pi over 2 to find a second point, and I'd be at 2, 0, 2, which would be straight up. And sure enough, that verified, like choosing those couple of points verified that I'm rotating the correct direction. Another way of doing that would be to use the dr in a moment. So questions about this? Very good. All right. So we're making headway. So step 2 is to find dr. This will just be 0, comma, negative 2 sine t, comma, 2 cosine t. And then step 3, we can sub and integrate. So our integral, that is the circulation of f dot dr, will be the line integral from 0, or the definite integral from 0 to 2 pi of f, let me write it this way, f dotted with, what's the thing that's going to come over here for our dr? What's going to go here?
Is it gonna be the curl?
Yeah, it's going to be this dr thing. So
Yeah.
we're going to end up with like a 0. Ooh, just running out of, there's just not enough space on the page. 0, negative 2. Can I go s for sine and 2c for cosine dt, at least temporarily? I'll come back in a second and substitute in for sines and cosines. But there's one of these components is really, really nice. What's the nice component?
0.
It's 0.
0. And so if you go way back to the beginning of this thing, notice we're going to be dotting this horrible vector field with 0, comma, negative 2 sine, comma, 2 cosine. So what's going to happen to all of that garbage?
Goes away.
It's just going to go away. So we can just leave all that stuff alone. We don't have to worry about anything there. So this will be the integral from 0 to 2 pi of the second component, which would be, remind me, what's x here?
2.
Yeah, x is 2. So this will be 4 times 2 cosine. So that'd be 8 cosine.
T.
8 cosine t times negative 2 sine t plus x squared is going to again be 4. Z squared is going to be 4 sine t. Did I do this right? So that would be 16 sine squared t. Times 2 cosine t. Did I do that right?
Could you scoot the paper up a bit, Dusty?
I can try. Try to keep multiple things showing. Let's see. Y. Yeah. I feel like I've got a typo in my notes online. I'm going to have to look at. And all this is dt. And at this stage, it's just a bunch of writing, right? So it's already 10:51. And so let me simply leave it here and make sure that the notes are posted, but for that last bit of integration. And so rather than working through it, let me just simply repeat the main point. The main point is that if we're evaluating the surface integral at the top, we were able to change this using Stokes theorem into a line integral, and then we're just working through all of our same line integral techniques from before. And in this particular case, one of the beauties of the line integral version is that we got rid of having to deal with anything in that first component. And it just sort of worked out really nicely. So that was kind of cool. So I hope you're all as stoked about this particular topic as I am. I hope you are excited at the fact that we are almost done with this quarter, with this class. And perhaps also excited about the fact that there's an entire book and movie trilogy, I believe, that's about our last topic of the class, namely the divergence theorem. So you need to do a little bit of homework this weekend and watch some divergence movies, a little bit of post-apocalyptic stuff. Go for it. But tomorrow we'll talk about it. And Frank, I hope you thought the Stokes theorem stuff was straightforward. I think that the divergence stuff is even more straightforward. So we get to finish in kind of a nice way. Thanks everyone again for a wonderful day. I look forward to seeing you all tomorrow. Feel free to hang on the line if you have any questions. Take care, everybody.
See you, Dusty.
Bye, Dusty.
Take care. Joseph, do you have some questions?
No, I was just hanging out for a little bit.
Cool.
Yeah, well, thank you so much, Dusty.
Thank you, and I will see you in class tomorrow, okay?
Yeah, sounds good. Bye-bye.
Take care. Bye-bye.